Hello and welcome to the UVU CS3060 Lecture 1.7, where I demonstrate how to save data to persistent storage and also read data from persistent storage. Well, let's get started. So a little warning before we start with this. This is a somewhat complicated topic. There's going to be a lot of reading documentation and trying to figure out what we want to do, simply because we're going to be writing to system calls that are not necessarily the easiest to work with. And then I will show you ways you can work with writing files that's a little bit easier. So let's get started. First thing I want to do is I'm going to want to open files for reading and writing. So I need to find out how that's done. I'm going to check my what is for open. And this is our first experience where the open API is actually represented in three different sections. We have section 1, section 2, and section 3 POSIX. Now, generally, the higher up it is, the more general the description and the easier to understand and how to use. So let's go ahead and start with section 3 POSIX and see if that man page is going to help us. So I'm going to do man 3 POSIX open. And we can see here's our open command. Now open's fairly straightforward. It takes a path, but then it takes these O flags, and we need to figure out what those O flags are. But then it will take other arguments that it doesn't have listed on this, so now we really need to read the documentation. Also, we're going to very likely need two different header files to make this work. So let's take a look below. I'm going to find out first what this O flag is. So I'm going to look down here. I notice that O flag is first mentioned here. Okay, it tells us that there's a way to set this O flag. Values of O flag are constructed by bitwise inclusive OR of flags from the following list, defined in this particular header file. Applications shall specify exactly one of the first 5 values. So we need to at least do one of these: read only, read write, search, and write only. Well, if we're just going to write data, let's use write only to start with. So at least we know one flag. Let's look at some of these other flags that they have. This one will append. We don't need to append at the moment. This one will set a particular file descriptor flag. We're not particularly worried about it. We do need to use the creation flag. So there's a second flag we need to use. First one is up here, the O write only, and then O create. We don't need to use O directory. There's desync is not necessary now. There's lots of other things. All we need to worry about is O create. But look at that description. Most of this is about the permission bits. We need to make sure we set the permission bits, and it tells us to see sys.stat.h to figure out what those permission bits are. Okay, sounds like another man page to me. So I'm just going to say, what is sys/stat.h? And here we are. We have a man page for this. So let's go ahead, man. Let's go ahead and put in the section 7 POSIX sys.stat.h. Now, this is actually describing the header file for a structure called the stat structure. So a lot of this isn't necessary, but we're specifically looking for what are called mode bits. And down here, this mode T type has several bits we can OR together. We need to give the file a certain set of permissions, such as, do we give it all the permissions, such as read, write, and execute? Well, it's just a simple text file, so we don't want the execute bit. which means we probably want to use something like the read bit and the write bit. I could do it for the other types, and we'll talk more about permissions, but let's just worry now about the permissions we need to access that file. And that's these two guys right here. So we've got this, the write, and the read. So now we've got 4 flags that we're using. Let's see if we can remember them. Now, let's just start with opening a file. I'm going to go ahead and create source code, right? I need to first include standard I/O because I am planning on, actually, yeah, we'll include standard I/O just as habit. We also need to include that sysstat.h because we need those mode bits. And then for open itself, we need to include fnctl.h. All right, so let's create our program. All right, argv, and we're just going to create the main body that just simply returns a 0. Now I want to write this program so that it takes data prompted by the user and writes it to the file. So I at least need one parameter on my command line, which means I need to check argc. If argc is less than 2, I need to provide some sort of message. And what should that be? Let's make it the usage. %s so we can print the command that they typed, and string. Right, and argv sub 0 because we want to print out the command, and then return an error value. So we want to use open and get a file descriptor. Now file descriptors are integer numbers. So we're going to start with an integer, and we're going to open, and now we need 3 parameters. The first one is the name of the file. We'll call it data.txt. We now need to OR the two flags that we saw earlier. And the first one is O, write only. And then we need to OR it with O, create. And the third parameter are the mode bits that we want to use. In this case, it was SIR user. And OR it with SIW user. That gives this file the read and write permission when it's created for the user alone. All right, so that's open. Now, before we actually write anything, let's just simply close this. Let's write a very simple program that opens and closes the file. Now, I can already tell you that this program is broken, but I'm going to show you how to fix a broken program. But that's a pretty simple program at this point. We're just simply opening a file and then closing it. So we write this, and we make my write program. Oh, I misspelled a header file, so let's change that. It's FCN. See? So we go ahead and write that, and there's still an error in here. It's actually more of a warning. The program still was created. It's telling me that close hasn't been defined. It means I don't have the right header file in place. Well, let's take a look at close. So man 3 POSIX close. So we do need to include the unistandard.h to be able to close file descriptors. So let's do. Excuse me. So I'm going to modify my source code file and add one more header file, the unistandard header file. All right, now that I have all my header files in and everything looks good, let's go ahead and make write. It'll be common you'll use an API that you haven't included a header file for. The man pages will generally help you. So if we take a look at our directory, we have write and write.c. When I run the write program, oh, there's my usage message. So let's go ahead and type in a parameter and then take a look at our disk. And there's our data file. Let's take a long look at this. A couple of things to notice. There's no data in here. We didn't write any data to it. But also, we got our mode set, so it's a read-write file. For now, I'm just going to delete data.txt, and I want to now write. So what does the write API? That's what is write. So there's a 3POSIX write man page. There's actually 4 man pages for this. So we'll use 3POSIX write. It uses the unistandard header, so we're good there. Write requires, in the simplest case, 3 parameters. The file descriptor that we got from open, a character or byte buffer, and that's going to be the string that we want to output. That's in argv sub 1, but it also requires a size. Well, there's lots of ways to get size, but we're going to use probably the most basic. We're going to write a function that figures out how big a string is. So we'll give ourselves a size variable. I'm also going to create a character pointer because I'm going to loop over my string. I'm going to say for p is equal to argv sub 1 and size is equal to 0. Yes, you can do multiple initializations. I'm going to keep going so long as p is not equal to the end of string character. And I'm guaranteed to have that end of string character for every string in argv. And then I'm going to increment both of these, both p and size. And within my loop body, I do everything, so I can give it, within my loop condition, I do everything. So I can go ahead and simply put a semicolon in there and let it loop till it finds a null. After that one line of code, after line 17, size should contain how many characters are in argv sub 1. So I should be able to perform the write. Now I'm going to capture the output of the write and actually print out what I got. So write, and I'm going to go ahead and write to our file descriptor, argv sub 1, and the size that we gave it. And then after we've closed it, let's go ahead and print out bytes written %d. And let's just take a look at what the write function or write API did for us. Now we're writing basically to the operating system at this point, and that's one of the reasons this is so difficult. So make write. Let's make sure we've deleted our data file. We have. So write, and let's go ahead and give it some data. If I want a space in my parameter, I have to use the quotes around it. And it says it wrote 9 bytes. 4 for sum, 1 for the space, and 4 for data. If we take a look, there's our file. And if we take a look at the file, there's some data. Now, one thing that this doesn't have is it doesn't have an end-of-line character. Well, that's not what argv provides. We're going to have to provide that ourselves. So just one more quick fix to write. Let's go ahead and perform a write to file descriptor of the end of line character. That's only one byte, and now we can do count ++ to increment that. And actually, let's just do it. Let's do it properly. Count is equal to count plus the return of write. So we'll make write. It builds. How about we do clear? There we go. And we run write with more data. Oh, actually, I'm going to remove the old data file. And so write with more data. Now it says 10 bytes are written. And if I take a look at the data.txt file, now it has a pleasant little carriage return in there. Whew. Took a lot of effort to do that. Reading isn't much easier. Again, we're going to use open, but now we're going to not use the create flag and just simply use the read flag. And if we look at our, let's take a, what is read, man read 3 POSIX. Oh, 3 POSIX read. And we can see the read API takes a file descriptor, takes a buffer, and takes the maximum number of bytes that the buffer has. Now we don't know how much our buffer is going to contain, so we'll make a nice big buffer. So I'm going to go ahead and create a read.c. It's going to include standard IO.h. It's going to include unistandard.h for the open API. It's going to include sysstat.h. And then it's going to include scntl.h. Create our main function. Don't really need the values from the main function. This is only just reading from a file we already created. All right, so we don't need to check. Let's just simply start right off, create our file descriptor, and assign open to our final file descriptor. We're going to open data.txt, and we're going to open it with the O read only flag. And that's it. That's all we really need to use. We don't need mode bits. Those are already set. We don't need the create. We're not writing to a new file. Just O read only. Now let's create a nice big buffer. Char buffer. Let's make it 100 bytes. And we're going to go ahead and find out how many bytes are read from the file. And we're going to perform the read. Now, I'm going to assign to count the return of the read function, because what read does is it will take the number of bytes that it reads from this file descriptor. We're going to say we have a 100 byte buffer and we can't go beyond 100 bytes. Read is going to come back and say, great, this is how many bytes I've read. So we should be able to now print out what we read from the file. So this is going, let's go ahead and read from file %d bytes. And then let's go ahead and do a new line and print out whatever the string is and another new line. So we're going to print out the count, and we're going to print out the buffer. All right. Now you're going to see some crazy stuff here in a second. We're going to already have a problem with our code, but let's see what this does. So I'm going to go ahead and make read. It builds successfully. Now remember, we have the data file that we saw before. It contains more data. I'm going to go ahead and run the read program. Actually it didn't do anything untoward. It did exactly what we wanted to. It printed out the 9 characters here, and it printed out the carriage return that follows more data. So this program reads from that particular file. Now, there is a problem here. This problem may be best represented if I do this. I'm going to go ahead, and I know that I'm going to read 11 characters. So the first character is at 0, and the last character is going to be at 10. Now, if I put at buffer sub 11 a value, let's go ahead and put the letter X in there, and we make this, and we run it. Wasn't it 11? Maybe it's at... So we're going to do 10, 11, and 12. And make it. And run it. Okay, you'll see here that what happened was the XYZ remained here because more data, these 9 characters, the 10th carriage return, that was all read. So we read 10 characters in here. The problem is it doesn't put a end of line character. We need to put an end of line character in here to make it a proper string. Open doesn't do that for us. Now, how did I know that? Hard, cold experience. So if we do buffer sub count is equal to the end of string marker, make the read, and run the read. Now that XYZ is gone because we've properly terminated our string. So that was all fine and dandy, but boy, it was hard. So we're going to actually use a library that comes with the operating system that allows us to do formatting. Actually, one more thing, I'm going to show you one more tool that you can use. You can actually see system calls being made from a program by using a special program called strace. If you just simply type strace, what you're going to the program you're going to do, and the parameters, even more data, it'll give you lots of information. But what's important here is actually down here when the actual program is being run. First thing is it performs an open. And there's our file. Here's the flags that we used. And this is what it returned. It gave that particular open a file descriptor of 3. And here we can see the write API actually using this file descriptor to write our data, which is 14 bytes long. And it returns 14. And here's our write for our end of line, our carriage return. And it was 1 byte. And then we performed a close, which returned success. strace actually lets you see a lot of the things that are going on inside your program as it's making system calls. And we can run this same thing. Let's go ahead and run strace on read. And again, we see here that we're opening it as a read-only file, giving a file descriptor of 3. It's performing our read function with a 100-byte buffer, and it's returning 15. So watching the system calls is one of the debugging tools that you have to see if everything's working the way you expect it to. Well, now that we've seen those, let's go ahead and create 2 more programs very quickly. So I'm going to remove data.txt, but I'm going to check on an API called fopen. So man3 fopen. Now fopen comes from standard I/O, and we're already including that for printf. There's a whole slew of these formatted I/O commands. The fopen we're going to use has the path name, and it has a string that identifies the mode, which is a lot easier than trying to remember which bits you need to use. In our particular case, we're going to use the write, which truncates the file to 0 length, or create the file, so we don't even need to give in the create flag. All we want is to write to this file. So I'm going to go ahead and, let's look at fprintf. fprintf is actually part of the regular printf man page. fprintf is going to take not a file descriptor, and this is important to remember, but is going to return or use a file handle, and this is what we got from fopen. It's then going to look just like our regular printf. So let's go ahead and create fwrite.c. This is going to include standard I/O, and that's the only header we're going to use in this particular case. Int main. We're going to go ahead and include our argc, our argv. We're going to return 0, and of course, if argc is less than 2, then we don't really have anything to do. In this case, we're going to print a message. Like that. And print out the command that the user typed in. And return an error condition. So what can we do now? Well, we're going to go ahead and create a file pointer. We'll call this fp. And we're going to perform the fopen. Fopen of data.text, and we want to write to it. Wow, how is that for easy to use? Now, it's important to check, and we didn't do this in the previous program, but we're going to check if fp is equal to null, because that's when it's error return. Then we're going to p-error failed to open file for writing, and return 1. Otherwise, we're going to write to this. We're going to do fprintf, and we're going to capture, of course, fprintf. We're going to use our file pointer. Now we're going to go ahead and use the s file descriptor and argv, or the format specifier. There we go. So 3 parameters: our file pointer, the format specifier, and the variable that goes with that format specifier. And then we can printf. Let's close close r, and then printf wrote %d bytes count. So much simpler. But remember, this is going through a library to attempt to format our data for us. So I'm going to write that. I'm going to make fwrite. We've got some problems here. So it's telling us it doesn't like, it might help if this is not just a character array, but a character pointer array. If that's the only error I've got, then excellent. So make sure we don't have the data. We don't. fwrite. We need a string. We'll call this some data. And it said it wrote 9 bytes. I didn't put a carriage return. Shame on me. If I take a look, you'll see that data.txt actually has quite a few different bits, but it has the read-write for the user, which is important for us. So let's go ahead and take a look at the content. And there it is. There are some changes I can make to this. Clearly, I didn't include my carriage return after this for formatting reasons, but I also didn't include the carriage return in my data file. Remember, argv doesn't have carriage returns after each string, so I have to add it myself. But rather than a whole new line, all I had to do is change my format specifier, get rid of the old data, it says it wrote 10 bytes, and there's the data. Reading is just as simple. You just simply use fscanf. So if I go ahead and fread.c, just include the one file, include file, create and I don't need to check for if something's there. All I have to do is, using the file pointer again, open the file, fopen, and this time I'm going to open data.txt, not for write, but for read. Check to see if we had a failure, and if we did, we can go, we did have a failure, we can use p-error again, and I'll show you that in action. Failed to open file for read. All right, so now that we've gone ahead and checked that, we can go ahead and perform, let's give ourselves a buffer. So character buffer of 0. And let's go ahead and perform int count is equal to fscanf. And you're going to use the file pointer. We're going to use a format specifier, %s. In fact, let's do %s\n so that we get everything up to the carriage return, and then put in our buffer. Fclose, our file pointer, and then printf read %d bytes, %s\n count buffer. Make freed. All right, and making sure let's actually remove the data file and see if we can get an error message out of this. So if I run freed, it says it failed to open the file, no such file or directory. Pretty formatting. It makes you realize I should have done fwrite. And now we can go ahead and try to run fread. Oh, we smashed the stack. We've definitely got a bug in our code. Let's take a look at what we have. And there's my problem on line 10. I might want to actually give the buffer some dimension. Failed on that part. But I'm going to go ahead and make this. We'll go ahead and we'll just simply continue. Now it comes back as it read 1 byte. Well, we know that we didn't read 1 byte, but it read 1 element of my file. It read up to the white space. And so you can see here that when you have input that has spaces, the fscanf is just going to read one string. Well, there is other things we can do to make fread work properly. So let's go ahead and look at our source code again. And we can see here that we told it to read a string. And it did. It read a string of data up to a space, but not including the space. Well, there are other format specifiers we can use. In fact, let's go ahead and put in this specialized format specifier. We want to scan everything up to that is not a carriage return. Now this may look very strange, but let me tell you, the formatted stream APIs, including fscanf and fprintf, have many format specifiers that help find the particular string you want. And we're going to change this to reflect what we're trying to do. Our fscanf is going to return the number of elements that it found. And let's see what this one returns. So I'm going to go ahead and write and quit, make fread, and let's go ahead and run it now. Now you can see we read one string, and it read everything except the carriage return, and it read the entire string including all the spaces for us. Now how simple was that particular change? If you understand the format specifiers, you can do all sorts of things and do them very simply. So as we did with open and read and write, let's go ahead and use strace to see what our system calls look like. So I'm going to remove data, and I'm going to go ahead and run strace with fwrite, and let's put in here last data, and let's see what we get. strace is going to put lots of information out here, but the key here is the fopen still did a regular old open, got a file descriptor. That file descriptor was managed internal to that particular API. It then performs the write for my particular data. The write was called by the fprintf API, and then fclose did the close on that particular file descriptor. So we can see that system calls are still being made, but we have a higher level API helping us and hiding some of these details. So what happens if I strace fread? And you can see that again we're going ahead and performing the fstat or the openat. This time it's a read-only access. There's no creation, nothing like that. And then it goes ahead and reads the data using the read API. It creates a huge buffer to do that. There's a 4K buffer going on here, but it only read the word last in here. In any case, this is again an example of how our formatted APIs are not system calls themselves. They're library calls, and these library calls will eventually make the system calls necessary to perform the operation. This has been the persistence of data demonstration, and I hope that it has been a help. Thank you very much.